Hello students, this is Mr. Allen, and today we are going to look at areas of regular polygons, section 10.3. Our objective today is to find the area of a regular polygon. We basically have two big ideas today. The first one is simply, I think it's pretty intuitive, but it is a postulate, so this is something that we will not prove, and that is that if two figures are congruent, then their areas are equal. So if we consider these two triangles here, triangle ABC and triangle QPR, first of all, we're told that triangle ABC has an area of 15 square centimeters, and so the question is, what can we conclude about this triangle over here? We know this one's 15. First of all, we'll notice that this angle and this angle are congruent, this side and this side are congruent, and then these two angles are congruent. So the two triangles are congruent by ASA, angle side angle. And if they are congruent, the conclusion that we can draw is that their areas are equal. In other words, the area of triangle PQR also has to be 15 centimeters squared. So this is the postulate. All right, now this is the main idea of the lesson though today, and that's finding the areas of a regular polygon. And here is the formula. The formula for the area of a regular polygon is 1/2 the product of the apothem and the perimeter. Now first let's focus on the perimeter. By the way, here's the formula. The perimeter is just the distance around. So if you need to know the perimeter, you just add up all the sides. In this case, it's a hexagon, so you'd add up the 6 sides. The apothem, though, that's this segment right here. By the way, here's the definition of an apothem. It is the perpendicular distance from a center of a polygon to one of its sides. And I know that's a very unusual word, but that's what this little a is right there. The A is for apothem, and the P is for perimeter. I will derive this formula for you in class. So let's go ahead and just see how this formula can be used to find the area of a regular polygon. What is the area of a regular decagon? Decagon means it has 10 sides. The right. So the area is equal to 1/2 the perimeter times the apothem. So we need to find those two things. Well, it looks like that the apothem is given here, and it's 12.3. It's this distance here. Now the perimeter, we're going to have to figure that out. We see that this side is 8, which means this side is 8, and this side is 8, and all the sides have to be 8 because it's a regular decagon. So the perimeter is just going to be 8 times 10, since there's 10 sides, so it's 80 inches. Now we can go ahead and calculate our area, which is just going to be 1/2 the apothem times the length, or the perimeter. And I'm going to go ahead and use my calculator. So 0.5 times 12.3 times 80. And I get a final area of 492 inches in squared. Remember, we're doing area, so we're doing squared for our units. So that's the basic idea of this section. Area equals 1/2 the apothem length times the perimeter. All right, example 2. This one is, I'm actually not going to find the area. I just want to kind of give an example of how we find angles in one of these regular polygons. In this case, it's a regular pentagon. And it says the figure at the right is a regular pentagon with a radii and apothem drawn. And then it says, what is the measure of each numbered angle? So there's a couple ways to go about this. But what I want to do is I want to go back and review a couple of important ideas from section 6.1. And those were the polygon angle sum theorems, in particular this n minus 2 times 180. That's how you find the sum of all the interior angles of a regular polygon, or of any polygon. And then we can just divide that by n, since all these angles are the same because it's regular. So I want you to make a note of this formula here. This is what we're going to use. So in this example, Since we're dealing with a pentagon, n is 5. So we would do 5 minus 2 times 180 over 5. And again, I would encourage you to just use your calculator. So I'm going to do 5 minus 2, that's 3 times 180, and then divide that by 5. So we get 108. That's what this is equal to, 108. So that means that this angle here is 108. Okay, so since this is a regular polygon, these radii are going to bisect each of those angles. So I claim that the measure of angle 3 has to be 108 divided by 2, which is 54 degrees. So that's the measure of angle 3. I'm kind of working backwards. Here's angle 3 right there. Now you'll notice that we have a right triangle drawn there. We know that angle 3 is 54. We know that it has a right angle, so we can just subtract. We can just subtract 54 from 90, since those are complementary. And just to make sure I don't make any careless mistakes, I'm going to use my calculator to make sure I get the correct answer of 36 degrees. So there's the measure of angle 2. And then last but not least, we're supposed to find the measure of angle 1. Angle 1, I'll do it in blue here, is this guy. So how are we going to find angle 1? Well, you could just double angle 2, so that'd give you 72 degrees. Because it's 36 times 2, right? Now, another way you could have approached this problem is instead of starting on the outside of the outer angles, if you will, on the inside of this pentagon, you could have focused on these central angles in the center. You could have done 360. In fact, you could try that right now. Just do 360 and then divide that by 5, and guess what you get for your answer? That's 72. And so you could have started with angle 1 and then worked your way back, going to 2 and 3. So anyways, there's a couple of different ways to do it. I wanted you to see that. All right, last example. So hopefully you guys realize where honey comes from. It comes from something called a honeycomb. And here I've got an actual picture of some bees and some honeycomb. And it turns out that each of those cells are what we call a hexagonal shape. In other words, they have 6 sides. And they tell us that the length of each side of these hexagonal cells is 3 centimeters. And they want us to determine the area of each cell. So they want us to find the area, if you will, of this one honeycomb cell. Well, we will notice, or at least we'll assume, that it is a regular hexagon, which it is. And so we're going to use our formula that we've been focusing on, which is 1/2 the apothem times the perimeter. Now we know that this side here is 3, so let's focus on the perimeter first. So if that's 3, and there's 1, 2, 3, although there's 6 sides, right? So the perimeter is just going to be 3 millimeters times 6. In other words, the perimeter is going to be 18 millimeters. Now we need to do the apothem. I'm going to tell you right now, the apothem is the tough part on this. And the reason it's the tough part on this one is because now we're going to have to go back, and I'm going to refer to my notes here because I want to make sure I tell you the right section number. Section 8.2. So to get this guy, we have to go back to section 8.2, which is on special triangles. So that's your 30, 60, 90, and your 45, 45, 90. Now, since this is a regular hexagon, let's go ahead and see if we can figure out what the measure of that angle is. And I'm going to do that up here. Remember, it's n minus 2 times 180 divided by n. This formula only works when it's regular. So in this case, n is 6. So I'm going to take my calculator. I'm going to do 6 minus 2 times 180. And then I'm going to divide by 6. So I claim that this is going to be equal to, in fact, let me just show all my work just to make sure there's no confusion. this turns out to give us an answer of 120 degrees. So this angle here is 120 degrees. Now, if that angle is 120 degrees, what would this angle right here be? Well, again, the radii are going to bisect that angle, so that's just going to be half of that. So that angle is going to be 60. In other words, we're going to have a triangle like this. I'm pulling this triangle out right here. We know that this is 60 degrees. We know that this is a right angle. And we know, now here's the thing, if this whole side here is 3, then what would just this piece, and let me draw that maybe in blue, what would just this piece here be? Well, it'd be half of that, so that'd be 1.5. Half of 3 is 1.5. This is what we call a 30, in fact, I'll put the 30 right there, it's a 30, 60, 90 triangle. Now, we know that this distance is going to be double the shorter leg, but the longer leg is going to be 1.5 times the square root of 3, and that's going to give us the apothem. So the apothem is going to be 1.5 millimeters times the square root of 3, and you know what? I might just leave that. I'm just going to leave that as 1.5 square root of 3 because that's not even the answer, our final answer. Now we're going to go back to our original formula up here. So our final answer for this, for the area of this hexagonal honeycomb cell, is going to be 1/2 times the apothem, which is 1.5 times the square root of 3. That's the apothem. And then times the perimeter, which we just found right there, which is 18. So we need to take our calculator and we need to multiply all of those things together. So 0.5 times 1.5 times the square root of 3 times 18. And you will get a final answer here of, I'm going to write it down at the bottom, 23.38, and this would be millimeters squared. That is the area of that hexagonal honeycomb cell, approximately 23.38. And again, we used, here's the big idea of this section, area equals 1/2 apothem times perimeter. And I think that brings us to the end. Thanks, guys.